Yeah, thank you very much. Thank you very much for having me. So today I will be presenting a survey or some highlights of a paper that we archived at the start of January last year. It's joint with Chen, who I believe is in the audience, Kabir Manali Rahul, Chris Parker, and Junwa Zheng. Um, so since I don't have much time today, I will not be talking about what's written in, is this violet? Purple, in purple, in purple over here. So this is an abstract result, out of which I will be squeezing some applications in representation theory. So this result, as you can see on the screen, is a general result about abstractions to bounded T-structures on essentially small triangulated categories. And you can see probably also this term, Niemann completion, which is quite a non-trivial construction that I will not have any time whatsoever to explain today, which is fine. But there's this other term called an equivalence class of bounded T structures that is somewhat easier to explain. So I'll just explain in a couple of words. So we announce two T structures to be equivalent to one another if they are finite distance from each other. So you will see this written down in a couple of seconds. So what are the applications of this in algebra? So in a sentence, the abstract result says if one has a small triangulated category such that its opposite category has quote unquote finite finitistic dimension at a certain object, then if you know that your category has a bounded T structure, that category will have to be equal to its completion computed with the metric generated by that object, number one. And number two, under the same finite finitistic dimension assumption on the opposite category of the ambient triangulated category, there can be only one equivalence class. All bounded T structures will have to be equivalent on any category lying between the starting category and any triangulated category lying between the starting triangulated category and its completion. Um, so as it turns out, it's very handy because you complete perf to dB mod for normal rings, for coherent rings, let's say. So in algebra, we get a very neat application very easily out of number one result from this purple box, which says that if you take an artin algebra and you know from before that the opposite algebra has small finitistic dimension finite, then the perfect complexes, the category perfect complexes is a bounded T structure if and only if the algebra has finite global dimension. Now, this as a result is something that most representation theorists will think that about which most representation theorists will or should think that this must have been known before because it looks very true, very truey without the finite finitistic dimension assumption. But it turns out this was not known before. There was a beautiful result by Adachi, Mizuno, and Yang from 2018 or 2019, I believe, who showed that if this same category has what they called an algebraic T structure, which is a bounded T structure plus some additional, I mean, that satisfies some additional properties, then that was equivalent to saying the algebra would be a finite global dimension. But it turns out if your category has a algebraic bounded T structure, then the finitistic dimension of your category is finite. So actually, uh, our result is a, let's say, a strengthening of their result. Like if you start from their starting assumption, you can reach the finite global dimension conclusion via our method also. I don't want to call it generalization, but although I did write generalization. So a very obvious question here that remains is whether number one is true without the finite findim assumption. And I mean, I have had some ideas over the past year about how to tackle this, but it is still open. Another thing, this follows from the second bullet point from the purple box. So if I have a ring, just a normal ring, and it is possible, as all of you know, I'm sure, to define small finite dimension of any ring. If I know for a random ring or associated ring with identity that is opposite ring has finite small finite dimension, and then if I take any category like between the perfects and, well, I wrote here K minus B are prods, but if you take R to be, I don't know, left coherent, you can write DB R mod. Uh, any category lying between perf and db, any triangulated category will have exactly one equivalence class of bounded T structure. So what it means is if you take two T structures like this, two bounded T structures, you should be able to find an integer T such that you can sandwich, let's say, the isle of the second one within shifts of the isle of the first one. I mean, this idea, this definition was proposed by Niemann, but there were, let's say, um, there, there were other papers that came before Niemann's paper that worked on some similar concepts. So here, what we get for free is that if you take R to be an Euclidean commutative ring, let's say a finite real dimension, then on dBr mod, all bounded T structures are equivalent. In other words, all bounded T structures are equivalent to the standard T structure. In other words, all bounded T structures are intermediate. I have to maybe check whether intermediate means exactly finite distance from the standard T structure or finite distance, or if distance one from the standard. I think it means finite distance from the standard T structure. So this is actually a very neat result to have. And back in May last year, Sergio Pavon, who I'm not sure if he's here, showed me a very interesting way of proving exactly this, just this, using the Alonso-Yerime-Saurin classification. I'm not going to go into what that classification is or what it classifies. But this was quite handy. And also, you might want to think like if your R is an artin algebra and this is dBr mod, what categories can you put between perf and dBr mod? You can think of like boundary drift categories of, let's say, the finitely generated coordinate projectives. So you can think of, I don't know, dB, R, G proj. But the problem is dB, R, G proj does not come with a standard bounded T structure because RG proj is not usually an abelian category. And when it is an abelian category, one can show that dBRG proj will then actually be exactly equal to dBr mod. So this is about the second purple point here. And in the remaining 3 minutes, let me say a few words about the singularity category. There's another category that one is often interested in. I spent a few minutes on this at a talk that I gave in China back in July, back in August. If some of you have seen this there, I apologize. So there was this idea of finitistic dimension of a triangulated category that I didn't define today. I mean, let's say it is a measure of smallness. It's a way to measure how small a category is. Like, no, not really. Like, if you know that a category has to be really small, you can imagine that that category must have finite finitistic dimension. The singularity category does not really fall in this category of does not fall in this class of categories that can be naively thought of as being small for some reason. But still, if I mean the singularity category is strongly generated, and we have a result in our paper that shows that if you have a strongly generated triangulated category where the strong generator satisfies a very standard Hom vanishing condition, then that category must have finite findim. But in this case, that the strong generator does not satisfy that standard quote unquote Hom vanishing condition. But still, one can show that if you assume that your algebra is Gorenstein, the singularity category will have finite findim, and of course the question remains if this is always true. And this is for a long time this has been a hidden result of Stovicek. I'm not even going to try with the accents. I'm sorry, Jan is in the audience. For a long time, it's been a hidden result of Stovicek that if the big finitistic dimension of the opposite algebra is finite, well, actually, it's an equivalent statement to saying that the singularity category is generated by the simples. I'm not going to say exactly what it means, by the simples, but from that, it implies that the finitistic dimension, small finitistic dimension singularity category, is actually finite. So it turns out this idea of a finite dimensional triangulated category has some credence even for singularity categories, because as you can see, one can find a counterexample to if one can find a singularity category with infinite findim, then big findim conjecture would fall. Thank you.
Oh, thank you very much, Rudradip.